on this computer. Okay, so in order for us to do a, 1 second. In order for us to do a coin flipping game, we should probably do a document that will allow us to flip a coin first, right? So let's write a very basic function, one that I hope that you would have some idea of how to write now, which is, or wouldn't be too hard, which is basically a function to flip a coin and tell me whether it's heads or tails. So, all right. Let's go ahead and write a function called flip. It's going to give us a evenly weighted coin. Now, obviously, flipping a coin is a random action, or at least it's pseudo-random, or it's not something we can predict the outcome just because of what we do it, right? We don't want, we're going to dodge the entire deterministic, consequential nature of the universe. Given the way things work, can we and electrical signals, if you're given all the conditions of something, can you predict the outcome, right? We're going to dodge that and say basically this is going to be a statistically random distribution of flipping a coin. In other words, 50-50. So there's a couple ways to do it, but we need the random library. Import random. Now there's a couple of different ways for us to flip a coin, to generate a flip coin. And let's go ahead and specify that when we flip this coin, we could return true or false. We could return 1 or 2, 0 or 1. Let's just go ahead and be very clear. We're going to return H for heads and T for tails. Make sense, everybody, so far? We're just writing function to flip a coin. So there's a classical way to do this. Right? Let me show you by importing random. Over here at the bottom of my screen, I've import random and random dot, I think next, not next, random dot float. Let's see, random dot rand. Random. There we go. Random dot random. It's always something different in different languages is the issue. You're right. I don't have these things memorized. Would you ever import inside a function if you only want that library to be available inside that function? That is an excellent question. You can do it, but traditionally we'd like to put all our things up there. So this will give me so random.random gives me a number between 0 and 1. Not sure if that's inclusive or not, but there are infinitely, if we're working in real mathematics as opposed to on the limitations of a computer, there are infinite numbers between 0 and 1, right? You can slice this as many times as you want. You can add more and more decimal points so that's perfectly fine. There's a whole cake of infinity in between 0 and 1, right? And so what we could do is that, hey, if it's between 0 and 1, one way we could do this is say, hey, if random dot random is less than 0.5, return heads. Else return tails. Right? That's all we're going to do to flip a coin, right? Makes sense to everybody? So I can go ahead and just execute these lines down here. I'm going to press enter. And then I'm going to go ahead and just type in flip once, just to show we've got tails, heads, right? But so that's one way to do it. It's a classical way. Another way we could do that is have random dot rand. Another way is that we could have random dot rand int between 1 and 2. Right? This gives us two numbers, and if it's equal to 1, return head. Otherwise, return tail. Make sense? Right, that's another way to do it. My personal favorite way to do stuff in Python, though, is just simply to say, hey, I've got these choices, which are head and tail. Return random dot choice of choices. Or let's go ahead and call this sides to be less confusing. And basically we're saying, hey, can you just choose one of these things randomly? this looks more readable personally, right? In my opinion. I don't know which one is more efficient. I suspect the one where we were doing functions was the most, where we were doing a floating point was the most efficient, but this is perfectly fine. So now we have something that is, and I am not lying here. This is very important. I have to be clear when I'm not lying in this lecture. That this is a random, that this is evenly distributed. Right? This is a fairly weighted coin. We can prove it's a fairly weighted coin, or we can observe that it's a fairly random coin by writing, of course, a Monte Carlo method, right? By saying, hey, heads is equal to 0, trials, right? This is a very basic Monte Carlo method, just to confirm that this function over here, it's going to have an even chance of heads or tails, right? Because there's nothing, me flipping 3 coins in a row, tails, 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 and heads, tails, tails, those are equally likely outcomes, right? Everybody agree with that? That's equally likely there. So to confirm it, we're going to go ahead and let's go ahead and just remember how to do a Monte Carlo approximation, which is that I'm going to just simulate this some number of times. We've got 1,000,000 times over here. So we are going to go ahead and say for blank in trials, in range trials. So we're going to do, some number of these. Heads plus equals, okay. Heads plus equals 1 if flip equals heads. Make sense? We're going to flip the coin. If it's equal to heads, increment heads by 1. Print heads divided by trials. Right? And this should be approximately 50%. It's not going to be exactly 50, but it's close. And if we run this again, we'll see that it's slightly below, slightly above that time, right? And we can get more and more accurate by adding more and more trials. So if I do 10 more trials, it's going to take 10 times as long, but we get another digit of accuracy here. Right? So this is close enough to, exact here. This is close enough to a fair cost as we're going to get. With that being said, who would like to volunteer to play a coin flipping game with me? Any takers?
Don't do it. It's a scam.
It is a scam, but I'm not gonna play for money or anything. Actually, we're just playing for the sake of learning.
If I win, will I get an A?
We've got Charles, who's goes ahead. I like how you think you're gonna win. Very positive there. Charles, would you like to play? Okay, so here's the game we're gonna play. So we've already talked about how basically if I flip 3 coins in a row, if I flip 3 coins, right? Heads, tails, heads, heads, tails, 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 tails. Those are all equally likely outcomes, right? There's 8 total outcomes we could have for flipping a coin, right? For flipping 3 coins in a row, right? Make sense? So we got heads, 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 tails, heads, tails, heads, right? And then we've got, stop autocorrecting, heads, tails, tails, right? And then we've got the reverse over here, tails, 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 heads, tails, heads, tails, and then tails, let's see, what's the last one? Oh, tails, heads, heads, right? Those are our 8 possible outcomes of flipping 3 coins in a row, okay? Following me so far? Okay. So who's ever deciding to play with me, I want you to pick one of these functions, and then I will pick one, or I will pick one of these you will pick one of these combinations, and then I will pick one of these combinations, right? You get first choice because it's only fair that you get first choice since you're new to the game. I'll pick one. They're equally likely to occur if we flip 3 coins in a row. And what we're going to do is that we're going to flip coins until the winning sequence occurs. And whoever sequence comes up first is the one person who wins. Okay. So Charles says he wants to choose heads, heads, tails. Okay. Okay. So let's go ahead and see. So I'm going to go ahead and choose the sequence. Tails, heads, heads. Okay. Tails, heads, heads. So let's go ahead and see which combination comes up first. So let's go ahead and write a function to do this. Def game player 1, player 2. Right? Because we want to play this game a couple times, right? So let's go ahead and write this out. So we've got, let's go ahead and write this out. Game, we've got player 1. So we've got player 1 sequence, we've got player 2 sequences. We've got, and we're going to go ahead and do like our, let's go ahead and do flips is equal to an empty string. And while, yes, Laser. You want something to what? You want something to drink? You were just downstairs with Mama.
I want to drink up here.
But you want to drink up here. Oh.
I want to. But I want to.
So while the last 3 coins of, so we're going to flip 1 coin at a time. Okay. So while the last 3 coins of this sequence is not equal to player 1 and the TV stopped. Equal to player 2. So let me just finish writing this loop. Flips plus equals flips plus equals flip a coin. All right, so that just simply adds on to the end of our sequence. And now we will, and then once we're done, actually, let's go ahead and, actually, I'm going to move this over here. I'm going to move this out. I'm going to instead make this a while true loop instead. Normally inadvisable because that's an infinite loop. But what I'm going to do instead is that after every flip, what I'm going to do is I'm going to ask, hey, did player 1 win? If so, we'll return a 1 for player 1 winning. And if player 2 wins, return 2. Otherwise, we're going to keep going. Yeah, you might want to go open up your task manager and kill it. So let's see. So we've got flips, true. So everybody understand this? Great. Give me 1 second to get. Oh, yes, I do want it to be equal. Excellent catch there, right? Because I was flipping the conditions from my while loop. All right, give me 1 second. Annie? Laser, where's your water bottle? He came up and wants something to drink.
He didn't want anything I offered.
He wants it to drink upstairs. All right, so now we've got this. So let's go ahead and play ourselves a game. So let's go ahead. So Charles chose the combination of You know, and if we were this in real life and wouldn't have to social distance during a pandemic, we'd be flipping actual coins. But let's go ahead and print out game. And Charles's choice was heads, tails, and mine was, let's see, tails, heads. So actually what I'm going to do is I'm going to go ahead and I'll return flips. I'll return what the sequence was, and then I'll return the who won. So if we run this game, well, still got my trials here, so we'll go ahead and comment that out for next game. But we see that tails, heads. I won that game. So can I explain what exactly the while loop is doing? This while loop specifically just runs forever until we hit a return statement. Return kills a function, so it would break the while loop. Okay, and what we're doing is that we just keep flipping a coin until the last three things of flip, the last three coins we flip are equal to either Charles's winning combination or my winning combination. So we flipped, and this was nobody. So then we take a look at this three. Now that we flipped one more coin, and it was tails, heads, which is my combination. So I won. So let's go ahead and run this again. I've got some pretty good luck, I'd say. Shucks. I'm just winning this like crazy. Hey, Charles, would you like to choose a different sequence? Oh, there you go. You won that one. That one went on for a while. So the question, of course, is that we don't know who's going to win in the long term, unless we play a lot of games. In which case, the statistics will become very, very apparent. Would you like to? So, Charles, are you still there? Oh, long term, they are not statistically 50-50. Remember, this is a scam. I presented, you see, I presented a true fact, and then I built stuff. I built a mountain of falsehoods over that true fact. All right. Would you like to go ahead and flip a coin? Or choose a different sequence, or would somebody else like to choose a different sequence? It is because of that combination. So choose another sequence, somebody. Tails, heads, tails. Okay. So you choose tails, tails. I'm going to go ahead and I will choose, let's see, heads, tails, heads. Here we go. And if we run this now, player one wins, player one wins, player one wins, player two wins, player two wins, player two wins. It's not the reverse. Not necessarily the reverse. I mean, but let's go ahead and see what happened here. It's not the inverse either. It's actually a very interesting rule that I'm following here. But let's go ahead and see the statistics rather than playing this one at a time, right? We can just Monte Carlo approximate this sucker. Okay, so for this in range of trials, rather than doing this, okay, we are going to do so game is equal to sequence and winner, right? Because we had two returns here. Okay. If winner equals 1, okay, if winner is equal to 1, then we'll just go ahead and count wins is equal to 0. Wins plus equals 1. Okay, and so what we're going to do is that we're going to print wins divided by trials to see what player 1's chances of winning, and player's 2 chances of winning are basically the inverse of that, which would be wins. Rather, let's go with 1 minus wins divided by trials. Right, so this would add up to 1 total. So we're going to go ahead and play that. That doesn't seem very nice. Highly implausible there. Oh, the function returns. Oh, yes, the function returns 1 and not 1. Thank you. So what you need to do is notice that I'm using a slice here. If I'm using a slice, then I never have to worry about out of bounds exceptions. It's a nice feature there. So those are about even. Those two are about even. Heads, tails, heads versus heads, tails, heads. Did I choose my thingy wrong? Yes, I did. So in this case, let's see the optimal move for me. No, I didn't choose it wrong. It was heads, tails, heads. Huh. All right. So interestingly enough, it's about 50-50 here. Let's go ahead and take a look at our first combination, which was what? Heads, heads, tails. And then I chose tails, heads, heads. That one was way lopsided in my favor. But all these three have, if I were to flip 3 coins, each of these have an equal chance of appearing, right? So what's going on here? Let's try another combination. Let's say, I'll give you another example. Let's say so some of you were saying, okay, I'm just going to choose the reverse. So let's go ahead and do heads, heads, heads. Well, what I would choose instead in this case is I would choose tails, heads, heads. And you'll see if I do that, I have an 87% chance of beating you. Whereas you have a paltry 1 in 8 chances of winning. In fact, you only win if you flip 3 heads. If we flip 3 heads in a row from the very beginning, and that's actually a good point to see here, right? You only win in this scenario if you flip 3 heads in a row in the beginning. Why? Well, let's take a look. If you flip head, 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 you win. But if you flip head, head, tail, then let's say we flip any number of tails in between it, right? It doesn't really matter. Nobody's going to win. But as soon as we start flipping heads again, it's going to be my win. And as soon as we get 2 heads, I'll win because my 2 heads are always going to come before your 3 heads. So the only way you can win that one is by flipping 3 heads at the beginning before a tail comes up. Because as soon as the tail comes up, essentially we're in a sequence where tails, heads, heads is going to come before heads, heads, heads. Make sense? So I presented the rules, but what happens is a bit different than what I described here. Now, for instance, let's go ahead and choose another one. Let's go ahead and do head, head, tails. In which case I would flip, let's see, I would do tails, heads, tails. Or tails, heads, heads, rather. Tails, heads, heads. There we go. Tails, heads, heads. Okay. So what that's going to look like is, let's go ahead and run that and see what the statistics are. 25% of the time versus 75% of the time. Let's see what happens. So that means there's 2 ways you can win. and you have to get them off. So one of them is by flipping heads, heads, tails in the beginning. And another way of doing that is by doing tails. Well, if you do tails, heads, heads, then I win. So another way of doing that is flipping a bunch of heads and then a tail. But as soon as you flip a tail, if you didn't flip 2 heads before that, then it's going to be my win eventually. Everybody see that? So this is actually a bit of a scam. This game is a scam, a total scam, because as long as you're choosing first, essentially what we're doing is I'm playing rock, paper, scissors with you, but you're telling me what you're going to throw before I throw my thing. So this is a game called Penny's Game. And Numberphile has a wonderful video about it. Was invented by Walter Penny. And basically, the idea here is that, let's go ahead and see. We've got, so these are the plays to make. So notice basically the underlying portions are the same. What we do is that basically we take, so the way the second player makes his win to trump another person, to trump another player's, is to, he basically takes the middle coin, flips it and moves it to the beginning of the sequence, and then cuts off the last thing. So here, as we can see, for this one, we take this guy, move it to the front, or take this guy, flip it, copy it, move it to the front, and move the other 2 there. So here, heads, heads, tails, we have the heads, heads from here, the heads, heads over here, and then flip this coin. So the third coin doesn't, you ignore the third coin when you're creating your counter. So here, the fairest odds are if we do tails, tails, or tails, heads, heads. It is not a fun game for the, well, it is if you're a scammer. But notice that the only way we could kind of figure that out was by running a Monte Carlo approximation, because I told you true, but completely, I told you true information that was completely out of context, right? The context was any one of these sequences, if we flip 3 coins, is any likely to come up. But the game we were playing was not, was not flipping just 3 coins. We were flipping coins until we got this sequence. And these sequences can be arranged in such a way that one is more likely to occur before another if you're just looking for 2 of them. Right? It is a subtle difference. Simply put, do not play games with people when you are inebriated and in a bar. Generally, somebody is going to try and make bank, especially if they've got a grin on their face and are telling you there's even odds. Right? And remember, in gambling, the house always wins, except in blackjack, in which case playing perfectly and using card counting can actually give the player an advantage depending on the rules. Blackjack is the only game that is profitable for the player in the long run if they can do card counting, which they catch counting, they'll kick you out, or they'll just simply send a very attractive looking fellow or lady over to distract you. So anyway, let's go ahead and so I if you couldn't tell, I really enjoy these kind of scams because they twist statistics on ourselves. I like these kinds of things where basically our intuitions are seriously wrong. Another one of these cases that we're not going to look at here, but that's called the Simpsons Paradox, not named after the Simpsons, although there's plenty of other stuff here, which is basically concatenate string. I'm not sure why. We'll try a different game here. So let's see. I wanted here. Baseball statistics is a bit easier to see, right? Some person might have a better. So here's the batting averages for two people, right? This person had a better batting average in 1995 and 1996, right? So you would think he'd have the better batting average overall for those 2 years. But in fact, Derek Jeter had a better combined batting average for those 2 years because of the, as you can see, there's a disparity in the number of at-bats. So this is another one of those fun statistical paradoxes. It's been used in lawsuits, such as the UC Berkeley gender bias case in 1973. Or rather, they used 1973 statistics there to show that just because there was an overall thing did not mean there was a bias in section by section, which was very interesting. But these are statistics are great at being able to deceive people. So let's go ahead and play another game, the game that I had described earlier. Yesterday. So not yesterday, the day before that. Tuesday, the day before yesterday. Okay, so let's go ahead and take a look at that. I got to just pull it up. Now, this game is from the book. So these examples I'm looking at are from the book How to Cheat at Everything, which is a fun book. Which is a book written by a scammer or former scammer or ostensible former scammer. All right, so let me go ahead and download it because I opened it yesterday, but I did not save it to my desktop. Okay, and now I'm going to go ahead and open it so that I've got my rules. All right. So here is our game that we are going to play today, our next game. This one is going to be, it's very similar to our other game because guess what? It is going to be a card game. All right. Select 5 cards and 2 black cards from a deck. Shuffle it and lay it out in a line. Shuffle and lay it out in a line. Can you flip 3 cards at random? Or can you get 3 red cards at random, right, before you hit a black card, right? If you flip over 3 red cards, you win. If you flip over anything that's not a red card, you lose. Make sense so far? So basically, we've got 5 red cards, 2 black cards, right? And the scammer typically introduces this as a scam, saying, or not as a scam, as like a fair game or one that you have a greater chance of winning, right? Because you'll have even odds or better than even odds because, of course, your first chance is 5 and 2, right? And this is completely accurate here. Your first chance of getting a card, of getting a red card to a black card is 5 to 2. There's 5 red cards, 2 black cards, completely accurate. So if you get another card, then your second choice is 4 and 2. Your third is 3 and 2. So each of those, so those are all completely accurate. But then he'll tell you the lie. So 5 and 2, 4 and 2, and 3 and 2, all those are above even chances of winning. So obviously your total chances are, they've got to be above even chances for winning, which they're not. Those are conditional probabilities. Now, you don't know how to do those if you haven't taken statistics, and that's okay. Because guess what? Monte Carlo is here to save the day because we can just simply simulate this. Okay, so we're going to make this very easy to simulate. Instead of like just choosing them at random, we're just going to choose always the first 3 cards. We're going to choose the one in index 0, index 1, and index 2, because that's as random as anything else, right? So we're going to choose those cards. And if they're all red, we win. And if any of them are black, we lose. So let's figure out the statistics for this game. Okay. So I'm going to call this game 5 and 2. Okay. 5 and 2. Doesn't need any inputs, right? So what we're going to do here is let's first create our deck of cards. So our deck of cards is equal to, and again, we'll make this really easy for ourselves. I'm going to create, let's go ahead and first I'm going to make sure this works, right? Because it always gets a bit tricky with replication. Okay. So 5 and 2, we'll create a red, 5 reds. I'm going to be lazy here, right? That creates 5 reds and 2 blacks. Okay, 5 reds, 2 blacks. And then what we're going to do is we're going to do random dot shuffle to shuffle the deck. All right, and we're going to go ahead and print it out right now just to confirm that we've got something that looks like it's working. So it does appear that we are getting different sequences each time, right? Make sense? So we've got 5 and 2. All right. Why don't we make it easier for us to see? I'm going to turn it into a string. Deck is equal to dot join. So I'm going to glue all these individual elements together using the empty string. This will just simply make it easier for us to read. Or at least, in my opinion, it will make it easier to read. And certainly it will make it easier to check. 5 and 2. So there, it's burb. And there we go. We've got our statistics. And so what really this comes down to is not like, can we pick 3 cards, but what are the chances a black isn't in the first 3 cards? So let's go ahead and basically, so we will just simply, we'll return a true if we win and a false if we lose. So let's go ahead. If deck so if the first 3 cards of the deck are equal to red, 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 return true. Else return false, or we can just simply skip all that and simply say return. Use double equals there. Return this if statement, sorry, this Boolean statement over here. Return whether or not this is correct or not. If it's true, if this evaluates the true, then the function is true, we win. Otherwise, we return false. So let's go ahead and print 5 and 2. And let's see how often, and let's see what happens. Oh, got to call it, right? I got to actually invoke the function when I write it out. Let's see, where did I get my error? Stop share. Where did I, nope, not stop share. Where did I get my error? Nothing, false, true, false, false, false. Yeah, it might be an unlucky streak here. I mean, I did win the second time, right? Okay, there's another win. My luck's going to turn any moment now, right? Gambler's fallacy, which is that a streak of bad means that a win is more likely to occur next time. This is a statistical fallacy. Games are so long as games are independent of each other. As long as games are independent actions and statistically independent, you're as likely to win one game as any other. How do I make it keep running? I'm going to put it in a for loop. So let's rewrite this for loop over here. wins trials. We're going to go ahead and play 5. So let's go over here and do, this one's actually going to be even shorter to write. If 5 and 2 equals true, I don't have to put in equals true. I could just put in true. If 5 and 2 wins plus equals 1. So the first thing that will get printed out is our win ratio. The second thing that's going to be printed out is how often we lose. So we won 28% of the time. And we lost about 70% of the time. About 30-70 of the split. Increment it to we do 1 million of these games. And we see that it's somewhere around 28.5% chance of winning. So this game isn't actually fair because, well, if I go ahead and just boot up Python for a second, let's see. What's the chances of 5? So we've got 5 out of 2 chances of, so the ratio of 5 to 2. All right, so we've got a chance of basically getting, our first card is what? Choosing any card out of the, our first card has a 5 and 7 has a 5 and 7 chance, right? Make sense? Our first card has a 5 and 7 chance, but then our second card has a 4 and 7, has a 4 and 6 chance. And then our next card is a 3 and 5 chance. And why didn't you know it? That number is very close to the winning rate that we actually had. Right? The chance of getting the chances that are, so when you're dealing with probabilities, by the way, you have ands, you multiply your ands. So the chance that your first card is good times the chance that your second card is good times the chance that your third card is good. That ain't particularly nice chances over there. Okay. But again, even if you didn't know how to do this, that was perfectly fine. You just throw it into a for loop and make it do that, right? So any questions on this so far? I'm just going to go ahead and I'm going to go through and make sure I don't do the one that I've used as an exam problem in the past. That's all. So give me 1 second, because I might want to use that one as a quiz question. Because, you know, I have. Okay. Oh, yeah. Okay. Yeah, that makes sense. All right, let's go ahead and, yeah, I don't think I used any of them from here for a, yeah, I don't think I used any of them for my document over here for this. So let's go ahead. So there's a couple, so let's take a look at some other games in here. 9-card hustle. Add 2 more red cards. So we've got 7 red and 2 black. Shuffle them, put them in a 3x3 array. The even money bet is that you can get 3 cards in the straight line that are red. So in other words, 50% chance of getting you can get that basically once we reveal the cards, that you're going to have 3 cards in a straight line that are red. Let's see, another one. So the odds of flipping a coin fairly, I'm getting heads or tails, is 1 to 1 or 50%. And the bet they give you is that you will get 5 heads and 5 tails in 10 flips. What are the real odds of that occurring? Right? And this is a Bernoulli sequence, which is a famous thing in statistics. 3 coins. Flip 3 coins with independent flips. If they all come up the same side, then the payout is 2 to 1. Otherwise, the buy-in is 1 to 1. Since at least one pair of the 3 coins must match, this appears to be a good deal. What are the real odds? Well, again, 3 coins. if they all come, you know, so if they all come up the same side, then you win. Well, that's a 2 in 4. That's a 2 in 8 chance because we know the statistics for that. But the lie they tell you is, well, one pair of the 3 coins must be the same, are going to be the same, right? One pair of the coins is going to be the same, right? You've got 2 coins, heads, tails, and then your third coin, by the Pigeonhole Principle, not making that up if you don't know statistics, as per the Pigeonhole Principle, then the last coin must be will result in either you having 2 heads or 2 tails. The Pigeonhole Principle is the funniest named thing in statistics. If you have basically n pigeons, if you have n plus 1 pigeonhole, so if you have n pigeonholes, in other words, places for pigeons to go, and you have n plus 1 pigeons, then one of those holes is going to end up with 2 pigeons in it. That's the Pigeonhole Principle in a nutshell. It's very silly, but it's used to prove a lot of things in statistics, or in combinations. So here they're saying, okay, via the Pigeonhole Principle, you know that there's going to be 2 coins that match. So that third coin is going to result in being a 50-50 chance, but that's not true. Okay. So there are these games over here. So let's go ahead and do this 9-card hustle one, because this one will involve us having to use a 2-dimensional array to do this one, right? Or 2-dimensional list, a list of lists, right? So that will make it a bit interesting. So let's go ahead and work on this one. So def 9-card hustle. Okay. So the 9-card hustle, again, because I went over a bunch of stuff here, was we want to take 7 red cards, 2 blacks, shuffle them, and put them in a 3x3 array. And the bet is that you get 3 cards in a straight line. So let's first focus on creating this, and then we'll figure out whether or not basically this part is accurate. Okay. So let's go ahead and figure out how to create this. Well, first thing, we need 9 cards. So I'm going to grab this. I'm going to actually grab this over here. It's actually fairly easy to change this into a deck of 7 and 2, right? And now we've got our 7 red cards and our 2 black. And now we've shuffled them. But he says we want to put them in a 3x3 grid. So we got to do that. So what we'll do is that we are going to, there's a couple different ways to do this. We could use for loops, but I personally prefer to use slices because that makes it a lot easier. So what we're going to do is say we are going to make our grid. So 3x3 grid is equal to, and I'm just simply opened it up like this to make it easier to see. Our first row of cards is going to be the first 3 cards. So that's going to be deck 0 to 3. So 0, 1, and 2. Our next grid of cards is going to be 3 to 6. Deck is equal to, and then deck 6 to the end. Print, and now we're going to print our grid just to confirm that it is working. Again, never try to program these things in like one big go because you'll just end up, making a mess. I need to make sure that this is working. So let's go ahead and do 9-card hustle, call that. And so notice that we've got a list of lists here. So what I've done is that basically I've got 3 items in the list, right? So print deck. So what I've done is I've taken the first 3 items, grouped them together, taken the second 3 items, grouped them together, and took the third 3 items and grouped them together. So we've got this 3x3 grid. Make sense? think I've got. Why is the grid spaced the way it is? Because by default, we just print out everything in one line. I will go ahead, if I do this instead, for row in grid, print row, we'll see it's printed a lot nicer and much more what we'd expect for a grid to be. Assuming I stop trying to treat grid like a function. Make sense? Oh, why is it spaced? Oh, why did I space it out like this? Oh, just so I could, so it would be easier for me to write it one at a time. It's an option you have. It's an option thing you have when you're writing a list variable to break it up like that rather than trying to do it in one giant line. It's a pretty cool feature. I could do it in one giant line, but look how awful that looks. Right? It's the same thing effectively, but this is a bit easier to read in my opinion. Right? It's a stylistic choice. It doesn't matter one way or the other what you do. So we see that this works. So now we have to say, okay, essentially we got to do a bit of like a kind of a tic-tac-toe thing. See if we've got a winner with 3 in a row. Okay. So there's how many ways can we get 3 in a straight line? We can get going across this way, going across this way, going across this way. So we've got our 3 rows. If either of those are come up red, 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 hoorah. If any of the vertical columns come up red, 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 then we win. And if either of the diagonals come up red, then we win. So let's go ahead and write this out. So if grid 0, so if grid 0, if our first row is equal to red, red, let's go ahead and call this target because I don't want to keep writing this every time. Target is equal to red, red, red. Makes sense? So if our first row is equal to the target, or the second row equal to the target, or the third row now what's cool about this is, right, this is saying if grid 0, what is grid 0? It's this slice. Grid 1 is this slice over here, and grid 2 is this slice over here. So grid 1 is the first 3 cards. Grid 2 is the second, or sorry, grid 0 is the first 3 cards. Grid 1 is the second trio, and grid 2 is the last trio. So I could make it one big if statement, but I'm just going to check all the rows first. Return true. All right, next let's check the columns, which is unfortunately a bit trickier. So our first column, right? Well, let's see. Let's go ahead and grab a Wacom tablet and draw this out for us. Right? Come on. Really need a bigger desk, but it's hard to complain when your desk was free. Okay, so let's go ahead. I suppose I just wanted to be more explicit, especially when I'm writing things with like this. Let's go ahead and see. So basically, if we've got this grid over here, this professionally drawn grid, right? This is our grid. This and effectively this first row is basically these three items over here, whatever they are. And this second grid is these three items, and so on and so forth. Coordinate wise, this is row 0, column 0. Right, so 0, 1, 2, 0, 1, 2. So these are our rows. And these are our cols over here. So this is row 0, column 0, row 0, column 1, row 0, column 2. Making sense so far? It's the reverse of X and Y, right? That's the way it works in matrices and stuff. So row 1, column 0, row 2, column 0. And then it would be 1, 1, and then 2, 1, and then 2, 2, and then 2, 1 over. Sorry, and then 1, 2.
I want to watch something else.
You want to watch something else?
What are you doing?
I am showing my students how to cheat people out of money.
But I want to watch something else.
He's watching the new Netflix Magic School Bus right now. So anyway. Yeah, the new Magic School Bus, right? Netflix came up with a revival of the series. Miss Frizzle got her PhD and became Professor Frizzle, and now her sister runs the classroom. So anyway, so if we're looking at the first column, so we're basically going to look to make sure that 0, 0, 1, 0, and 2, 0 are red, red, red. Then we're going to look at 0, 1, 1, 1, and 2, 1 to make sure that's red, and so on and so forth. Okay, so let's go ahead, and I'll keep up this extremely garish thing over here. So you want to watch the real Magic School Bus? Let me be back. Now I'm going to put on the first episode laser. I'll just put. All right. Yeah, because he's been watching these things, he constantly surprises me with the amount of stuff he knows. I did not know he knew as many musical instruments as he did. All right. So if grid 0, and then the way we do 0, 0 is we do it like that. So if this, you want what? The sound wave one? I will, after we watch, after we do class, I will put on the sound wave one. Okay. So grid. So I'm making a new list out of these things. One, 0. 2, 0. If that is equal to our target, return lasers. Okay. And now let's go ahead and hit the insert key, see if that works. So now 1. Apparently the insert key is just not as friendly as it used to be. Okay, so now we've got that. And now we need our two diagonals, which would be 0, 0, 1, 1, and 2, 2 for the first one. So 0, 0, 1, 1, and 2, 2. And then the other one is 2, 0, 2, 1. And the order doesn't matter which I do those, like the order in which I arrange these, because we're checking to make sure they're all red. So 2, 0, 2, 1, 0, 2. And if none of those work, return false by default at the end. All right, so let's see if we've been hustled here. So let's clear out this annotation. Clear all drawings. Okay. So now let's go ahead and throw 9-card hustle into this file, into our trial. So again, it's very simple because we're just checking to see if we are winning or losing. So wins is equal to 0. If there's a stink bug, is it scary? Isn't 1, 1? Idris, what do you mean? Oh, yes. So if 9-card hustle is equal to true, print that. And so now let's go ahead and run this. Please work, please work, please work, please work, please work. Laser. Laser. Now is not the time to play the piano. So I must have programmed something wrong here, because we shouldn't be winning 100% of the time. Now he's turning my chair. Let's go ahead and see. So what have we done that's absolutely wrong here? So print. Let's go ahead and figure and do some really terrible debugging. What's wrong, Glazer? Do you really need me to get rid of that bug? Where is it? Annie? I see it. I got it. He does not like bugs. All right. 2, 3. So this should also be, so I'm not actually entirely sure what is wrong here. Let's go ahead and see. We know that I'm winning 100% of the time. So let's go ahead and see if there's one case that I miswrote over here, which is that it's always saying part 1 is correct, which is interesting. Okay. So let's see, random shuffle. Random pain in the ear. Oh no. No, I don't want that. I don't want Gmail. I want random shuffle Python. Right? So shuffles in place. Okay, that should be fine. So why is it that we've always got, oh, right, because there's only, of course we would win 100% of the time because 3 in a row. Oh, okay. The even money bet is you can find 3 cards in the straight line that are red. Okay, that makes a lot more sense. Okay, so what they must mean is rather than flipping over all the cards, you get to flip over only 1 row, column, or that. So you only get 1 choice, in other words. Because, of course, if we're printing out the entire grid, there's only 2 blacks. So you can put 1 on 1 row, 1 on another row. 3rd row would be completely open, right? So our real rates of winning this, so for this game, what we're really asking is none of this stuff. What we're going to ask is if the very, 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 very first grid, if the very, very, very first row, we'll flip that over just like we took the first 3 cards in our other example. If those 3 cards are red, then we'll win. Yeah, I totally misinterpreted that and was engrossed and distracted by other things. All right, so real statistics of this should be 1 and 3, I would think. Something like that. A bit better than 1 and 3. Let's see. And the reason is that, right, you've got 9 places to, you're choosing your first card, then your second card, then your third card. So you've got 6 out of 9, 5 out of 8, and then, right, let's go ahead and do that again. 6 out of 9 times 5 out of 8 times 4 out of 7. Interesting that that is the rate, though, because you do have a bit better because it's got to be in a straight line, which restricts it a bit, which is interesting. All right. So let's go ahead and do one very last one that we already partially written, which would be our Bernoulli one, which is what is, right? Oh, which is basically somebody saying to you, well, getting a coin flip is 50-50. So let's flip 10 coins. Obviously, if you flip 10 coins, then you've got a 50-50 chance of getting 5 heads and 5 tails, right? So what's the real rate of getting 5 heads and 5 tails? So let's go ahead and do def 10 flips. And this is again we're trying to see if we get 5 heads, 5 tails kind of deal. So let's first flip this 10 times. So flip returns a string, right? So 4 blank in range. I was thinking I could do replication there, but I realized I couldn't there. So 4 in range 10, do this 10 times. Our sequence is equal to the empty string. And then what we'll do is we'll do sequence plus equals flip the coin, right? But that very first function we wrote, right? Now what we'll do is that we will do, so now we're going to do our standard printing it out to see what we got. Our sequence house to see what we got. And again, let's go ahead and comment these out. Print 10 flips. right? So it wasn't getting 5 in a head, 5 in a tail. It was, could you get, or in a row, it was, can you get 5 heads and 5 tails total. So easy way. So let's go ahead and see if there's an easy way to do that. Let's go ahead and see sorted. So what would sorted seek give us? It returns a list. So this returns a list. So if I were to print this gives us a list where the string has been sorted. Okay. And then let's go ahead and turn that into it. You know, that's actually, Landon, that is a good point. Count is easier rather than trying to do some stuff with sorted. So one way we could sort it would be, I was thinking sorted and then check the slice, but count's an easier way to do that. Okay. I've just been doing slices so much today that I'm automatically just reaching for this for that metaphorical knife. So let's go ahead and say, okay, if count. So if seek.count h equals 5, and that's all we need to check, actually, because if you've got 5 heads, you've got 5 tails, right? Return true. Else return false. So let's go ahead and play and do this game. So see how basically it's just a function and then basically counting the results of the function here. Okay, so now if there are more than 2 outcomes, what you would do is create a dictionary to count the outcomes, right? For instance, if you're a D&D player and you want to figure out optimal statistics, without actually having to do hard math, a Monte Carlo method might be a good way to min-max your character. All right, so for blank in range trials, let's change this to 10 flips. Print out the output. And we see that we've got a 25% chance of winning this bet rather than 50. So yeah, this is so this is also, again, one of those things where it sounds plausible, but it's really not. Monte Carlo methods are really good like that. All right, so with this, I think I am going to go ahead and leave you with a question I wrote for my exam last time, and because I want to come up with something a bit similar. Oh, sorry, similar but simpler than what was on my exam. And if you want to get some extra practice on something like that, you can try, because this one I think would be a bit too much. So let's go ahead and see what was on the exam 2 last time around, which was last semester. So here we go, which is a Monopoly game. So the board game Monopoly. Everybody's probably played Monopoly at some point, right? Great game to end friendships and family bonds, right? You move around the board by rolling a pair of 6-sided die. Okay? Rolling doubles, which is if you roll 2 3s or 2 5s, right? You roll 2d6 in die terminology. You roll 2d6, and if you get and if you roll a double, like 2 3s, 2 5s, 2 6s, you get to roll again. Essentially, you get another turn. If you roll another set of doubles, in other words, 2 doubles, you get another turn. But but if you roll 3 doubles, you immediately go to jail, right? So getting 1 double, you get 2 turns essentially. You roll a second double, you get 3 turns essentially in 1 turn. But if you roll that doubles one more time, immediately you go to jail. So what we want to do is simulate a program that simulates 100,000 Monopoly turns, and I say that basically an extra roll due to double counts as a turn. So you can interpret it as that as part of the turn or something else. I would do it as part of the turn, where a turn is a single roll. Where a turn is a single roll of the dice or more if the user rolls a double. Your program should print out, yes, ignore the parentheticals, that just made it more confusing. Your program should print out the percentage of rolls without a double, the percentage of rolls where you get 1 double, thus getting 2 turns, 2 doubles, or 3 doubles. In other words, what is the likelihood that your turn is one of those turns that makes you go directly to jail? Right? And then the way I graded it on the exam was 10 points if you could just do, it looked overwhelming, but the way I pointed out for people on the exam was you get 10 points if you simulate 100,000, pairs of dice rolls. That's it. Forget like counting them, just roll the dice. Then handling the double, how often you get doubles, handling 2 and 3 doubles in a row, and then presenting the data in percentages, right? In other words, giving me data in the way that I asked, rather than telling me the total numbers. So so if you want to try that, or you want to get more practice on Monte Carlo methods, looking at board games is an excellent way to do that. Speaking of games, the homework you're going to be working on is a dice game, which is basically it's one of those games of chicken, essentially. It's called Pig. Essentially, you roll a die. That's your score, and then you get the option of rolling until you rolling and keep adding to your score. But if you hit a 1, you lose all your score for that turn, or you can bank the score that you get at any point. So the question is, what our Monte Carlo approximations are going to simulate is, what is your kind of the optimal strategy for playing this game of Pig, which can get pretty in depth.
Professor, for Pig, we only have to kind of just finish the last problem, right? Instead of all the
the mini problems ask different questions, such as what is the chances of you winning outright in Pig? In other words, if you decide to go for broke and just keep rolling the die until you hit 100 points, what is the chance that you'll actually succeed? In other words, what's the chances that you'll be able to roll the die and get to 100 points without rolling a single 1? So you do need to work on a lot of those smaller portions, but each portion you do builds up to the bigger program.
Got it. So when we submit it,
you'll want to submit all your files. Yes.
Oh, got it. Yep. Thanks.
Okay. So with that, by the way, class is dismissed. And before I leave class, I will definitely upload this onto GitHub. So let me go ahead and do that. So stop recording.